Welcome to the second to last colloquium of the summer, which means I'm free in 2 weeks. All right, so today's speaker is Shinsuke Imada, and he graduated from the University of Tokyo in the Department of Earth and Planetary Sciences. His PhD was on the topic of energetic electron region and its acceleration mechanism in magnetotail reconnection. After his PhD, he moved to the National Astronomical Observatory of Japan and joined the Hinode mission as a member of the EUV imaging spectrometer team. And now he works at the Institute of Space Earth Environmental Research in Nagoya University as an assistant professor. His main topic of research is magnetic reconnection, and today he's talking about project for solar-terrestrial environment prediction towards predicting the next solar cycle. So.
Thank you very much. Thank you very much. Is it okay? Okay. Thank you very much for giving me talking at this colloquium. I'm Shinsuke Imada. I'm from Nagoya University. Okay, this is a collaborating work with several people, and today I would like to talk about the project for solar-terrestrial environment prediction, which is especially towards predicting next solar cycle. That's which I now involving. So I want to briefly introduce myself. As Rebecca already mentioned, I got a PhD in University of Tokyo 2006, and at that time I'm doing the magnetospheric physics, and especially I'm interested in the energetic particle acceleration and magnetic reconnection process itself. And after PhD, I moved to NAOJ, National Astronomical Observatory of Japan, which is the main institute for the Hinode. And I involved in Hinode Science Project. So Hinode is almost 10 years. We have a Hinode 10th meeting in Nagoya. And I'm also 10 years old for solar physics, actually, yeah. And after NAOJ, I moved to ISAS, JAXA, and now I'm working at Nagoya University. And our institute is slightly modified, changed. So I very briefly introduce our institute. So our institute established last October. It's 2015 October. So originally, it's a Solar-Terrestrial Environment Laboratory and Hydrospheric Atmospheric Research Center and Center for Chronological Research. It's difficult to pronounce. And combine these three, now we have IC. It's an Institute for Space Environmental Research. So it's rebuilt. And roughly saying, the faculty number is 30 and 11 and 5. So now it's 46. It's getting bigger and bigger. So I'm not sure why our government say more bigger and bigger. But now our institute is getting bigger. So it's our number is 46. And about IC, our topics is from the sun, interplanetary, and magnetosphere, and also ionosphere and atmosphere also, and sea. Also, we also do the sea some research. So I think it's very similar to the NCAR, and not so large as the NCAR, but I think we can. The NCAR is a very good competitor and also collaborator, I guess, for us. So that's our institute. And as I mentioned, my major is a magnetic reconnection. And so I do a lot of work for solar flare or coronal heating. So mainly I studied plasma acceleration and or heating. And these are recent papers. It's almost, most of them are related to the magnetic reconnection physics. So if you are interested in these, first one is non-equilibrium ionization during the solar flare. And the second one is, the first one is Earth is magnetosphere particle acceleration physics and non-equilibrium ionization. And the third one is fundamental physics, but viscosity, finite viscosity boosting the magnetic reconnection. It's very interesting paper. So if you are interested in this one, please let me know. And the fourth one is Hinode and Iris observation of the in this very sunspot wave propagation. So this is also very interesting. But these are my main topic. But today I would like to talk about the next solar cycle prediction study in the category of the PSTEP project. So it's a project work. So what is a PSTEP? Project for Solar-Terrestrial Environment Prediction, we call PSTEP, was launched in order to improve the predict capability through synergy with the basic science research and the forecast operation. So there is a death ballet. So we want to connect each other. That's one of our important point. And PSTEP is a nationwide research collaboration supported by a grant in aid for scientific research on innovative area from MEX Japan. By this project, we seek to answer some of the fundamental questions concerning the solar terrestrial environment system and aim to contribute to building a next generation space weather forecasting system. That's the final goal for us. And we have 4 kind of group. And the first one is a space weather forecasting group. And the second one is a solar storm group. So it's mainly solar physics. And the third one is a geomagnetism group. So it's a magnetospheric physics. And these two are relatively short-term, space weather, something. But in the fourth group, solar cycle and climate group we also have. This is a longer-term variation prediction of the space weather. So that's actually I involve everything, but mainly I involve in A04, group number 4. So this is a group for solar climate and solar cycle and climate group. And there is 3 topics. The first one is a solar cycle prediction. So detailed analysis of solar magnetic fields measurement by the Hinode or SDO or infrared spectrometer at NAOJ. And predict the solar cycle 25 using the surface flux transport model based on the observation parameter. That's our strategy. And I don't want to go detail in the solar radiation and the cosmic ray group or solar influence on the terrestrial climate. So we also want to know how the solar variability affect the terrestrial climate. That's also our target. And so this is a solar cycle 25 prediction group member. So this is me. And this is our postdoc in our university, Iijima-san. He is very good at numerics, so it's very powerful guy. And the third one is very famous. I think most of you know him because he was here last August. So Hideyuki Hotta. And we also have some student in Nagoya University, so we work with them. And this is an old member of ours. And let's go to the cycle prediction. So far, many people already do the kind of solar cycle prediction. So these are the last cycle and current cycle. So last from the prediction from the last cycle. This is the horizontal axis means relative sunspot numbers. And vertical axis means several papers name. So just put several prediction result. And yellow line means answer. Current cycle relative sunspot number is this part. So the prediction result is not so bad, but not so good. That's, I think, the current status of the cycle prediction. So how to predict the solar cycle? That's one of the important point. And one of the good method to predict the next solar cycle is estimating the polar magnetic field at solar minimum in current cycle. So this figure shows dipole moment at the end of the cycle n, and relative sunspot numbers of cycle n plus 1. So it's mean next cycle. It's very, there is a very linear correlation like this. So dipole moment at solar minimum is strongly related to the relative sunspot numbers for next solar cycle. So this, by using this relation, we want to predict the next solar cycle. That's our strategy. And to estimating the polar magnetic field, we are planning to use the surface flux transport model. So surface flux transport model is solving this kind of equation, magnetic field time derivative equation. So and this is roughly saying diffusion convection equation of the magnetic field. So this is a model and this is observation. So year and latitude and color is the magnetic field. So roughly speaking, it can be trace the magnetic field transportation. So like this. So solving the temporal evolution of the magnetic field by using the observation, because one of the our strongest point is we have a Hinode. Hinode has a very high resolution observation of the magnetic field. So that's one of our strongest point. So by using the observation of the source regions, I mean the sunspot magnetic field or flow measurement, meridional flow or differential rotation, whatever, those kind of flow put into this equation, it's getting more better prediction we get. That's what we think. And actually, many already some people predicted the next cycle. For example, Upton and Hathaway 2014 or Cameron et al. 2016 already predict the next solar cycle, and same way, I mean, using the surface flux transport model. So we have to do as far as possible because already there is some result. So from their result, cycle 25th seems to be relatively similar activity level as a current cycle. But we want to do by ourselves, I mean, with our code. And we built a surface flux transport code, solving this equation. And if we use a usual spherical coordinate system, the grid spacing is very small, like this in polar region. So because of the CFL condition, the time step should also getting smaller and smaller. So to avoid that problem, we use a yin-yang grid. So like this, yin and yang and combined together. So this is a yin space and this is a yang space. And so information is propagating from this way and this way. I mean, connecting each other by from this boundary. So we can solve the two space and information propagate each other. That's what we have done. And we test Bowman et al. 2004. This is they do not use observational data. It's artificial sunspot number or sunspot latitude dependence or separation and tilt angle or longitudinal dependence they use. It's artificial, I mean, not observational. So it's very easy to test, do that. And this is a result of the retrace of the Bowman et al. This is a Bowman et al. Result, and this is our test result. So, this is a grid space, 79, 223, and so yin and yang we have so two space, and so this is a resolution, and we solved the 50 years, and the time step is a 6 hour we used, and in our workstation in our laboratory, it's not so like a supercomputer. It's not, but it's just a interprocessor, 18 core, some machine, and we can solve it 7 minutes. So our code is not so bad, and result is we have to check more detail, but it looks like okay. But actually, I think we mistake one thing. The polarity is opposite. So I think it's just mistake for our. And we also try to do the data simulation, SOHO MDI. So this is we also do the data simulation flux transport calculation, and now yellow and blue, and it's later it's getting to this part is blue and this part is getting yellow. So I think so far it seems very nice. So we have to more carefully see the result, but I think it's the model itself is working very well. Yeah, now it's getting blue, and it's also getting yellow. So it's polar field is reversed. Okay. So this is a model summary for our current stage. We have developed the surface flux transport code to predict the next solar cycle. We have finished several tests, for example, Bowman et al. 2004, some data simulation, and so far it seems very good. So we are now ready to predict the cycle 25 by using this surface flux transport code. So next, I want to talk about some input parameter from the Hinode observation or SDO observation. So observation part, we have to do the several things. The first one is we want to know the answer. So we have to observe the polar magnetic field itself. This is a very advantage for Hinode. I will explain later. And the second one is the flow, meridional flow or differential rotation or those kind of flow. We should measure by the observation. And also we are trying to understand more carefully about the sunspot decaying. So actually today I do not talk detail about the sunspot decaying, but we carefully do the statistically doing the sunspot decaying process and check the sunspot decaying process is isotropically or not non-isotropically. So and find at least the leading sunspot. It seems there is a kind of some anisotropy. They transport much more toward the equator side. That's if I have a chance to talk about this next time, I will talk that. And also we want to do the flux emergence also, kind of this, because this is also very important topic for us. So today I want to, because not so much time, so I want to concentrate on two topics for polar magnetic field and flows, meridional flow or differential rotation. So let's go to the Hinode. What is the Hinode? Maybe most of you know the Hinode, but there is three telescope, SOT, XRT, and EIS. So actually, my main part is EIS, but today I want to talk about the SOT observation. So solar optical telescope can observe the magnetic field with a very high resolution, 0.2 arc second or something. So it's a very good resolution. And today we use spectral polarimeter observation, SP observation, and NFI observation. We use two observations. So why high resolution is important for the polar magnetic field? Because the resolution is very severe in high latitude. This is a schematic illustration. So this is a SDO HMI continuum observation, and this is a Hinode SOT. I guess you can distinguish those two. So high resolution is very important to if you want to see the polar magnetic field. And this is a very famous result of the Hinode. So maybe many of you know this result, polar magnetic fields observation with the Hinode like this. So one of the very astonishing, very important finding is so magnetic field is very concentrated even in the polar region. So it's up close to the kilogauss level in some part. And there is a very strong patches in the magnetic field in the polar region. That's a very important finding for in Hinode 2007. So it's difficult to see, but so we do these kind of observation continuously. So we already detect polar reversal with the Hinode observation. And I hope you can see this is the north, and this is the south. And this part, I think you can see the red, orange, or something kilogauss patches around here, and getting lesser and lesser. And there is not blue, but it's some marginal state in current stage. And for the southern part, it's blue. Almost there is lots of the blue patches there, and getting redder and redder. And now 2006, it's getting the patches getting red. And if you go to more carefully analyze, this is a distribution of the polar magnetic field, and horizontal axis mean how strong the magnetic field is, one patches. So this part, I mean, this 20 or 21, this means kilogauss patches. And on the other hand, 15 or 16 or 17, that's very not strong one. It's messy one. So if you go to the reversal, the polar, strong magnetic field is, black one is negative and blue one is a positive. So the weaker one, we have a positive and a negative also. But kilogauss patches like that, the strong patches, there is only the unipolar signature. And time goes by, it's getting weaker and weaker for the kilogauss. But this messy one, it's not so much different. So the polar magnetic field reversal should occur by the changing of the kilogauss strong magnetic patches. That's a very important finding for Hinode observation. Okay, so let's go back to our strategy. We want to estimate the polar magnetic field and solve the magnetic field transport in the solar surface flux transport code. So we need several parameters, for example, differential rotation or meridional flow. So today we discuss differential rotation and meridional circulation velocity. So first, we use SDO observation because many people are already doing from the SDO observation. They observe the meridional flow or differential rotation. So we starting from that. And we also use a very classical technique, local correlation tracking technique. And I think most of you know about this one, but just for briefly introduce that. First, let's decide a strip, this region, and make the correlation with those three, and define where is it. This strip move to where is. So we can observe like this. So roughly speaking, Com et al. 1993 or Hathaway 2010 use the same method. It's slightly different, but almost same. So we use that. So this is a SDO result. The upper panel shows a differential rotation, and bottom part is a meridional flow. And we fitted by the following function. It's a Comet or do that, 1993. This is a function, and this is for meridional circulation function. And this is a fitting result. And this is our result, and this is a Com et al. Result. And if we compare, the value is almost, roughly speaking, it's same. So our analysis is not so bad currently. So we can observe this part. And we also do another kind of technique. I already introduced a local correlation tracking technique. And we also try to the magnetic element tracking. This is just tracking each magnetic field element and derive the velocity of each magnetic element. That's another technique. And if we compare the local correlation tracking and magnetic element tracking analysis for HMI data, and this is a latitude and this is a differential rotation velocity. So it's roughly speaking, it's same for the magnetic element and the local correlation tracking. But low latitude around here, magnetic element tracking is slower, and high latitude it's very consistent with those two. So if we apply to the low latitude, it's something we have to care more carefully. And this is a meridional flow result. And in the meridional flow result, mid latitude is almost same around here. But high latitude, magnetic element tracking looks much faster. But we have to care more carefully deal with this. We need more data and more check about this result, I think. So, okay, that's a low latitude analysis, but we want to discuss about the higher latitude, I mean, with Hinode observation. So let's go to high latitude region. So as I mentioned, we use a Hinode observation. It's a 0.2 arcsecond resolution. And in current analysis, we use a sodium line. And okay, this is a Hinode polar observation. And so this is already projecting result. And so I hope you can see some magnetic field going this way. So it's rotating. And we track each element. First project like flat going like this map, and detect several magnetic fields and track it for 3 hours later and derive the velocity with these two. So this is a Hinode result. Sorry about little bit difficult to. This is a South Pole result, and this is a North Pole result. It's just a one observation. I'm sorry, we didn't finish every Hinode data. Just only one. Now currently I have just one sample, and so this is a minus 90 degrees. So it's a pole, South Pole, and this is a 765 degree. And this is also 90 degrees. This means a north pole. And the blue one shows a meridional flow, and red one shows a differential rotation. So differential rotation also same like this, and meridional flow also we can observe. And if we put together with the Hinode and HMI data, it's going like this. This is a Hathaway et al. Result, and this purple line shows a Hathaway et al. Result. So our result is very consistent with in the differential rotation in the mid latitude, I mean low latitude region. It's quite almost same result. But if we go to the higher latitude with Hinode observation, it looks like much more slower like this. So differential rotation is getting slower in the what we originally expected. And if we go to the meridional flow, the low latitude is still we need a discussion, but it's roughly speaking, it's same order. Go like this. On the other hand, the higher latitude meridional circulation is still very, how to say, scattered. So we are not sure how to tackle with this result, but now we are thinking about the method and also the physics also, and we are now discussing the polar region meridional circulation is very important to understand more detail about the flux transport prediction. Okay, this is a summary. To predict the next solar cycle activity levels, we have developed the surface flux transport code by yin-yang grid, by using the yin-yang grid. And we have retraced the several previous research, and the results seem to be very consistent now, so far. We also determined the several physical parameters by Hinode high-resolution observation, and we almost finished the preparation for prediction. So we will have a prediction result very near future, I hope, and I want to, discuss more about that kind of analysis result with HAO people. Thank you very much.
Questions?
So the polar magnetic field, you saw that you have lots of kilogauss magnetic field structure in the flux range about 20 to 21 maxwells or so. Yeah.
This one.
Yeah. So then what is the average field strength then? Like as you find so much flux there and field strength kilogauss. So what is the then average field strength?
Average. Oh, okay. Yeah. Average is not now I have, but 400 or something. You mean the large one? This one? Totally.
Yeah, total. Yeah, total.
Okay. Yeah, that's okay. Yeah, it's very consistent with the HMI observation. I mean.
So then average field is about 10.
Average field is okay. Very consistent with the HMI observation. So it's maybe in the stronger case, 16 or something, 10 or, yeah. Sorry, it doesn't come.
Any other question? Michael.
So it's interesting that you find the polar rotation rate slower than the extrapolation from low latitudes using this sine squared and sine to the fourth fit. I think that is consistent with what helioseismology found from MDI.
Okay.
Back in the 1990s, but I'd have to check. But I think
okay.
Is your result published?
Not yet.
Okay.
Yeah.
Maybe I can refer you to the paper and you can have
Okay, thank you.
But heliososmology measurements are not reliable towards the pole. Do you think? I missed the point you're going.
Are you asking Michael?
Yeah.
Or are you asking?
I'm asking to you.
What was the question?
We told that it's consistent with the heliososmology measurement, but it's not reliable in the high latitude. Heliososmic measurements are not reliable in high latitude because
They're less reliable. Above 75 degrees, they're not reliable. But I certainly think up to 75 degrees, you would see a similar trend below what I kind of tend to recall the Snodgrass kind of formula.
Is that from Jesper Shaw's?
Yeah,
paper?
the 98 one.
Yeah, we get the same results for tracking other features in the corona at those high latitudes.
Okay.
When your meridional flow, it's kind of interesting. I know that you said you acknowledge there's a lot of scatter at high latitudes, but unlike the low latitude, which is kind of anti-symmetric around the equator, you're actually seeing northward in both hemispheres. Do you think that's reliable at all? There's actually a poleward flow. A northward flow in both hemispheres.
Yeah. Yeah. Actually, we did more check. I think so.
So in one hemisphere, you kind of have a counter cell.
Is that possible? Maybe. That's
how
one.
many years data you have? This measurement, which year?
Okay, this is. I said this is. I'm sorry. This is just one time, 1 year. Yeah. So it's not enough, I think. So we want to do because Hinode is already have a 10 years observation. So we will apply that.
Yes, please.
Yeah.
Definitely. So what was the beam angle then? I mean, were you seeing both poles the same at the same time?
Yeah. So actually, this result is coming from the June, and this result is coming from December or something. So yeah.
March and September. What data sets are you using for the polls? Are they like repeated maps or something like that you can track things?
No, it's
or just a long-term.
Yeah, it's this is a observation itself.
Yeah. Okay, so it's a repeated.
Yeah, repeated.
Scan.
Yeah, fixed pointing and.
Yeah. Right. Any other questions? Yes.
Can you explain when the solar cycle is delayed starting?
That's very difficult to answer. Yeah. So actually, in our project, we also want to discuss about the cycle length itself, but it's not start. Just thinking, for example, magnetic quenching or those kind of effect we want to estimate, but it's still under discussion. Thank you.
Is that all?
Unless you have anything to show us about the asymmetric sunspot decay. Do you actually have anything you can show us? Or?
Sorry, I'm not now. I have,
okay.
But so we just do the more than 100 sunspot in leading sunspot. So just estimate the magnetic element detection and magnetic flux, and times velocity, and there is asymmetry or not. So it shows leading sunspot shows relatively going the equator. Yeah, that's our result.
Okay.
Yeah.
That seems to be all, I'm guessing. Somebody's talking in the back. No questions? All right, well, yeah, okay. Let's thank Shinsuke again.
Thank you.